Carbon. As you know, carbon is the backbone of all biological and organic molecules. It fits that purpose well because it can make 4 bonds. So it can, that's the most that an element can make, by the way, is 4. And so it can make a large variety of different kinds of molecules and chemical structures to make all the hundreds of thousands of different kinds of molecules that life depends upon. And another property of carbon is that it can form bonds that can store energy. And that's primarily what happens with photosynthesis and respiration. And that is the main way in which carbon is exchanged. Where am I? CO2 and H2O. Oh. Carbon is exchanged back and forth through the
that was me.
Through the biosphere. No. So that's the main way carbon is exchanged back and forth through the biosphere. Okay. So these, we've got the sinks here, but these are, and I'm only going to put them on this one because these are the same sinks that we're going to talk about throughout each one of these types of elements. And I listed on the title page. These are the spheres, of course, of the Earth. The 3 physical ones: lithosphere, hydrosphere, atmosphere, and the biosphere as well. So the biosphere is a much bigger part. We've talked about these other 3 quite a bit. The biosphere, of course, is a much bigger part of what we're talking about in ecology. In this case, it does play a big part of carbon, and of course the biosphere, all things that are made from carbon, so that's crucial there as well. So we see that, of course, biological molecules are put together. They're put together by plants who carry out photosynthesis. So they actually, this equation right here represents both, by the way. That's why I've got the back and forth symbols here. So when it's going, which way is it going for photosynthesis? Left or right? Going this way or this way?
Be going left.
That is correct. Everybody clear on that? Left. The photosynthesis part of this equation is going this way. We'll go ahead and use green to represent that. And then the respiration part of it, use blue for that, is going from the left to the right. So you can see there, since these 2 processes are exactly alike chemically, they're just going in the opposite direction, that you can have a cycle going back and forth through there. Okay? So that's the main way in which carbon goes back and forth through in the biosphere between organisms. Yeah.
What does P stand for again?
P is for photosynthesis. Okay. So let me go ahead and put that up. Made green, of course, because chlorophyll, which makes plants green, is a big part of this process. So there we go. So that's biological processes that take carbon back and forth, and this is how they cycle between them. All right. Now, human impact. So that's a major issue here. That's what this course is all about, of course. And the main ways in which we affect this carbon cycle are things that we've talked about already, and that is through burning fossil fuels and then deforestation, because deforestation affects what? Well, before I write the arrow to it, what does it affect up here we just talked about? Less trees means less what process? Photosynthesis, right, photosynthesis. So photosynthesis takes CO2 out of the atmosphere, and particularly with trees, it takes it out for a long time, and respiration puts CO2 back into the atmosphere. Okay, so whatever encourages or discourages either one of those processes, either photosynthesis or respiration, there's a number of things that we as humans do that do those things. They're going to have an effect on the CO2 amounts in the atmosphere, depending upon which one of them affects. So deforestation is going to decrease photosynthesis, and a decrease in photosynthesis means less CO2 going into the atmosphere. And then, of course, that wood that's cut down is going to be either burned, which means that CO2 through combustion will go right back into the atmosphere, just like when you burn fossil fuels. Or if the trees sit there and rot, it'll go through decomposition. And that decomposition most of the time uses respiration to break down stuff, so the CO2 will also go right back out in the atmosphere. Okay? So we've talked about this quite a bit. I don't want to spend much more time on this. We talked about global climate change and stuff, and of course one of the things that we're mainly concerned with is CO2 in the atmosphere is the fact that it might be increasing the Earth's temperature. But I want to focus more on something else that extra CO2 that we're putting into the atmosphere may have an effect on. And that's based on the fact that carbon dioxide is water soluble. And if you've ever drunk a soda, which is short for sodium bicarbonate, that is you've experienced this. That's what the bubbles are, CO2. Carbonated beverages are carbon dioxide dissolved in water. And so it does that. It's much more soluble, for example, than oxygen. It can hold, quite a bit of CO2. The solubility of it does decrease as temperature increases. And we talked about this also when we were talking about global climate. The fact that if the climate of the Earth, the temperature of the Earth rises, that the CO2 in the ocean will become less soluble, and so more CO2 will come out, and therefore it could get warmer again, which would make the oceans warmer again still, more and more and more. What kind of process do we call that? What kind of feedback? Positive or negative? Positive. Positive feedback means it gets the effect increases more and more. Okay. So when CO2 dissolves in water, it goes through a little reaction, partial reaction to be completely honest with you there, but it forms hydrogen carbonate. This is also known as carbonic acid, which, by the way, this is why they put it into sodas, because acids are sour, and therefore this makes it acidified a little bit. It gives it that extra tanginess kind of flavor to it. But this isn't soda science, so we'll move on from that. But that's the basic reaction with CO2. This is how it dissolves into the water. So as an acid, I don't want to get into the details of acid-base chemistry, but the H's are going to come off, and then this CO3 ion is going to be dissolved in the water as what we call a carbonate ion. Okay. This is good because those carbonate ions, let's go ahead and write that in there in case you forgot your chemistry. Okay, carbonate ion. And this is good for a lot of the creatures that are in the ocean that have shells, because they absorb that carbonate ion and combine it with calcium to make calcium carbonate. Okay, we know this. We've got the piece of the Florida lithosphere that is calcium carbonate. Limestone's another word for it. There are large deposits of this in many places around the world. This is why we have our aquifer like we do. This is a crucial reaction that goes on in the ocean. So it's good that it has some of that in there, but the problem is that this also, of course, since this is an acid, overall extra CO2 dissolving into the ocean lowers the pH, makes it more acidic. We all know that lower pH means it's more acidic, and this will actually interfere with the calcification process because acids dissolve calcium carbonate. So there's it's a very fine, like many things in nature, it's a very fine balance between having enough carbonate ions in there for the marine organisms to be able to absorb them and build their shells, but to the point where it hasn't affected the pH that much, to the point where you have so much that even though you've got plenty of carbonate ions now, it actually makes it harder for them to carry out this calcification process. Now, this is true not only with exoskeletons with calcification, but calcification technically also is how skeletons harden. And although we haven't really seen in the ocean that being an issue with the fish and weaker skeletons, it is been shown in lakes that have a low pH because of acid rain, which of course is a stronger acid than your carbonic acid, but because of the acid rain of the nitric and sulfuric acid, you see fish in those areas. One of the effects you see is a fish have weaker skeletons, and the waterfowl, ducks, and also turtles. They're of course not waterfowl, but turtles and other reptiles that lay their eggs in the water. A lot of times their eggshells in those kind of acidified lakes are not as strong. Now, same reason, because of low pH, not exactly the same source. This is from CO2. The acidified lakes are more from acid rain, which as we know is different. But same thing, same chemical idea in that acids dissolve minerals like calcium carbonate. Any questions about carbon cycles? So we've got the basic back and forth of respiration and photosynthesis. You've got the human impact, which primarily of burning fossil fuels, putting carbon dioxide in the atmosphere, cutting down lots of trees. That also increases the CO2 in the atmosphere. And then you've got the issue of carbon dioxide dissolving in the water, and what that does, how that's affected by the temperature, and the fact that can acidify the oceans, and that can be harmful to organisms that make shells and stuff like that, as well as other things. There's other things I didn't go into, but it's lower pH effects. So that's kind of the many different things that are affected by that. All right.